From a simple falling apple to a rocket blasting into space, the exact same rules are calling the shots. Today, we're cracking open the physics toolkit that lets us predict the future of pretty much anything that's speeding up or slowing down. We're talking about the equations of motion.
So really, it all boils down to this one question. If something is moving, can we actually predict where it's going to be? And how fast it'll be moving when it gets there? The answer is a huge yes. And believe it or not, the tools we use are incredibly elegant.
Now, we could talk about things moving at a constant speed, like a car on cruise control. But let's be real, that's kind of boring. The really interesting stuff happens when velocity changes. When a car floors it, or you toss a ball up in the air. That's why we're focusing on constant acceleration, where things speed up or slow down at a nice steady rate.
To even start talking about this stuff, we need to speak the right language. And that language is built around 5 key variables. Think of them as the main characters in our story today. Once you get to know them, you'll be able to solve pretty much any problem that comes your way.
So, first up is S, for displacement. Now, this isn't just distance, it's distance with direction. Let's say you walk 10 feet forward and 10 feet back. You've traveled a distance of 20 feet, right? But your displacement is 0, because you ended up exactly where you started.
Next, we have U, which stands for initial velocity. This is just the speed an object has the very instant we start paying attention, the moment we hit the stopwatch. It's our starting point.
And, well, if you've got a starting velocity, you've got to have an ending one, right? So v is our final velocity, the speed of our object right at the moment we stop timing it.
And here's the real star of the show. A, for acceleration. This tells us how quickly the velocity is changing. Now, for what we're doing today, this number is constant. That means the velocity is changing for sure, but it's doing it in a super steady, predictable way.
And last but not least, T for time. This one's easy, it's just how long the motion lasts. So there you have it, our 5 key players, S, U, V, A, and T. Now let's see how they all dance together.
So, how do these 5 variables actually relate to each other? Well, they're all linked by 3 beautifully simple but incredibly powerful equations. This is your brand new toolkit for motion. The first equation is just so logical. It basically says your final speed is just your starting speed plus whatever change the acceleration caused over a certain amount of time. Simple, right? But so powerful.
Our second equation is the one that lets us find out how far something went. It's displacement. It takes into account where you started, how fast you were going, and how that speed has been changing. And see that little t squared in there? That's a huge clue that something really cool is happening on the graph, which we're going to see in just a minute.
And then there's the third equation. This one's kind of like a secret weapon. Look closely. Notice anything missing? There's no t. There's no time. This is your go-to equation when you have no idea how long the motion took, or you just flat out don't care.
Okay, so equations are one thing, but to really get a feel for this, let's see what it looks like. When you plot these variables, they create these really specific, predictable shapes that tell you the whole story.
Okay, let's imagine a car that's already moving at 10 meters per second, and then it starts accelerating steadily at 3 meters per second every second. Look at the pattern. After 1 second, its speed is 13. After 2 seconds, it's 16. It's just this perfect, steady increase. So what do you think happens when we plot that data on a graph? We get a perfect, straight, sloped line. This is a golden rule. If the acceleration is constant, the graph of velocity versus time is always a straight line.
And here's the really cool part, the aha moment. The steepness of that line, what mathematicians call the slope, it's not just some random number. It is the acceleration. For our car example, the slope is 3. That was our acceleration. The graph is literally showing you the physics. It's amazing.
What's so powerful here is you can see how these graphs tell a story together. Our acceleration is constant, so its graph is just a flat, boring line. But that constant acceleration builds up to create a velocity graph that's a perfectly straight, sloped line. And that steadily increasing velocity creates a position graph that's this beautiful, sweeping curve, a parabola. Each graph is literally the result of the one before it.
All right, enough with the theory and the charts. Let's put these equations to the ultimate test with something we see every single day, gravity. What really happens when you toss a ball up into the air?
So here on Earth, gravity is always pulling things down, accelerating them at about 10 meters per second squared. But if you throw a ball up, gravity is fighting it the whole way, slowing it down. So for that upward trip,
We just say the acceleration is -10.
And this is what's so elegant. The trip has this beautiful symmetry. On the way up, the ball starts out fast and slows down until its velocity is 0 right at the very peak. Then, on the way down, it starts from 0 and speeds back up. The physics is exactly the same for both halves of the journey. The only thing that changes is the sign on the acceleration. Negative on the way up, positive on the way down.
So there we have it. We've gone through the variables, the key equations, what the graphs look like, and even a real-world example. You now officially have a complete toolkit for tackling any constant acceleration problem you're ever going to see.
So how do you actually use this stuff? It's a super simple 3-step process that works every single time. First, just list out what you know. Write down the numbers you have for S, U, V, A, and T. Second, figure out your target. What's the one thing you're trying to find? And finally, you just play matchmaker. You look at your 3 equations and pick the one that has all your knowns plus the one unknown you're looking for. It's like a puzzle, and this is the cheat code.
I really want this to sink in. These aren't just some random formulas to memorize for a test. They are truly the bedrock of kinematics. They describe the fundamental nature of how things move in our universe, at least under this very, very common condition of constant acceleration.
And that leaves us with one final lingering puzzle. Our equations say that gravity should pull everything down at the exact same rate. So then why, in the real world, does a bowling ball always beat a feather in a race to the ground? Well, the answer involves a force we haven't talked about yet. And that's a story for another explainer. Thanks for watching.